Our journey tonight takes us far away to a distant, luminous ringed planet. We'll be exploring a few of its most intriguing companions, the icy moons of Saturn. These worlds, though seemingly small, hold incredible stories etched into their frozen surfaces. They whisper tales of ancient impacts, of hidden oceans, and of dynamic geological processes that defy our expectations. Let's begin with one such moon, a place called Dione. This moon, named after a powerful goddess from ancient Greek stories, presents a striking mix of old wounds and active geological formations. Its bright, reflective outer layer conceals deep, old scars and geological wonders that continue to puzzle scientists. Dione holds the position of the fourth largest among Saturn's more than 200 known natural satellites. In terms of size, it measures a modest 120 kilometers across, which is actually less than the width of Texas. Yet, despite its relatively small stature, this cold world contains secrets that continually captivate space researchers and astronomers. We are making our way to this distant, frozen sphere. It's a place where towering, icy cliffs dominate cratered plains, where mysterious, delicate-looking streaks stretch across its face, and where the constant pull of gravity has molded a unique world. The discovery of Dione, much like many other moons circling Saturn, dates back to the very first use of telescopes in astronomy. It was first seen by the celebrated Italian astronomer Giovanni Cassini on the 21st of March in 1684. Cassini, who was working from the esteemed Paris Observatory, had already located another of Saturn's moons, Apotus, a couple of years prior. He would go on to find two more of Saturn's satellites, Rhea and Tethys, further expanding our knowledge of that distant system. Initially, Cassini simply labeled this new discovery Saturn IV, indicating it as the fourth moon from Saturn based on its distance from the giant planet. It wasn't until 1847 that the English astronomer John Herschel put forward the idea of using the names of Titans from Greek mythology for Saturn's moons. This is how Dione eventually received its legendary name. The name is quite suitable, actually. In Greek mythology, Dione was a Titaness, frequently described as the child of Oceanus and Tethys, and sometimes even considered a partner of Zeus. Some ancient stories even hint that she was the mother of Aphrodite, the goddess of love. Just like her namesake from myth, the moon Dione would turn out to have surprising connections and relationships with other celestial bodies within the vast Saturnian system. But we'll delve deeper into those connections a little later on. For nearly 3 centuries following its initial discovery, Dione remained little more than a tiny speck of light when viewed through our telescopes. It was a mysterious world about which we knew almost nothing concrete. Even with the most powerful observatories on Earth, this faraway moon held back its secrets, revealing very few details of its true nature. All of this, however, would dramatically shift with the arrival of the space age, a new era of exploration. Our very first close-up view of Dione came from NASA's Voyager 1 spacecraft, which sped past the Saturnian system in November of 1980. As Voyager drew nearer, Dione began its transformation, changing from a simple point of light into a world with clear, distinct features and its own unique character. The images captured by Voyager, though limited by the technology available at that time, unveiled a moon possessing a remarkably complex surface. Dione appeared heavily marked by craters on its trailing hemisphere, which is the side that consistently faces away from its direction of orbit. The largest of these impact craters bears the name Eander, an enormous basin that measures approximately 350 kilometers in diameter. Other notable craters include Aeneas and Dido, both named after characters from Virgil's epic poem, the Aeneid. Yet, perhaps the most captivating discovery was the presence of strange, bright streaks that crisscrossed various parts of its surface. These features, which scientists affectionately called wispy terrain, seemed unlike anything observed on other planetary bodies at that particular time. However, with the brief nature of the flyby and the limited imaging capabilities, Voyager could only offer a tantalizing glimpse, merely whetting our appetite for more knowledge about this enigmatic moon. The spacecraft also took measurements of Dion's diameter, confirming it to be about 120 kilometers across, making it the fourth largest moon of Saturn, following Titan, Rhea, and Apophis. Voyager additionally determined that Dione possesses a density of approximately 1.48 grams per cubic centimeter. This density figure strongly suggests a composition primarily made up of water ice, along with a modest rocky component, most likely containing a small silicate core at its heart. But this brief encounter, while groundbreaking, ultimately left planetary scientists with more questions than it provided answers. What exactly were those mysterious wisps? How did Dion's surface come to be? What powerful forces shaped this distant, icy world over the Uns? It would require another spacecraft, one bearing the very name of Dion's Italian discoverer from nearly 4 centuries ago, to truly begin to unravel these profound mysteries. In July of 2004, NASA's Cassini spacecraft successfully entered orbit around Saturn, initiating what would become an incredible 13-year mission of exploration and discovery throughout the entire Saturnian system. This highly sophisticated spacecraft carried a comprehensive suite of advanced scientific instruments, tools that would completely revolutionize our understanding of Saturn and its many moons. Cassini carried out multiple close flybys of Dione during its extensive mission, approaching as near as 99 kilometers to the moon's frozen surface. These close encounters provided an unprecedented wealth of high-resolution images and a treasure trove of scientific data about this mysterious world. One of the most significant breakthroughs came when Cassini finally revealed the true nature of the enigmatic wispy terrain, which had first been vaguely glimpsed by Voyager. What had initially appeared as bright, streaky deposits from a distance were, in reality, exposed ice cliffs. These were the sheer faces of enormous faults, deep chasms cutting through Dione's ancient icy crust. These remarkable features, now officially called chasmata, are in some instances hundreds of kilometers long and several kilometers deep. The most prominent of these geological formations is Palatine Chasmata, a massive system of fractures stretching for more than 600 kilometers across Dione's varied surface. Other major fracture systems include Padua Chasmata and Carthage Fossa. In certain areas, these fractures cut directly through existing craters and other surface features, a clear indication that they formed relatively recently within Dione's extensive geological history. Dione's density measurements, meticulously gathered by the Cassini mission, further confirmed that it is composed primarily of water ice, but with a surprisingly significant rock component. This breakdown is roughly 40% rock and 60% ice by mass. This specific composition gives Dione a total mass of about 1.11020 kilograms. Based on this precise density and mass, scientists were able to confirm their long-held belief that Dione most likely possesses a differentiated interior. This means it has distinct layers, featuring a modest rocky core encased by a thick, expansive mantle of ice. The surface temperature on Dione is, as you might expect, extremely cold, averaging around 187 degrees Celsius. At such incredibly frigid temperatures, water ice behaves very much like solid rock does here on Earth, allowing for the stable formation of rigid geological features such as towering mountains, deep craters, and winding canyons. As mentioned earlier, roughly half of Dione's surface is dotted with craters, clear signs of countless ancient impacts. But perhaps even more intriguing than these impact scars are the areas where craters are noticeably absent. Certain regions of Dione show compelling evidence of resurfacing. These are geological processes that have effectively erased older features and, in their place, created smoother, flatter plains. These particular areas, predominantly located on the leading hemisphere, strongly suggest that Dione has undergone periods of internal activity, events that have refreshed and smoothed out parts of its ancient surface. But let's talk in more detail about Dione's impressive chasmata. This bright, exposed ice stands in stark contrast to the surrounding older surface material, which has been steadily darkened over billions of years by constant exposure to cosmic radiation and countless micrometeorite impacts. But what could have possibly caused these enormous, moon-spanning fractures? The leading scientific explanation suggests that they formed in response to global stress patterns acting within Dione's rigid icy crust. As Dione slowly cooled and evolved over immense spans of billions of years, its outer crust would have experienced powerful tension and compression forces. These forces ultimately led to the extensive fracturing we observe today. Some scientists believe these massive fractures might actually be compelling evidence that Dione once harbored a subsurface ocean, a vast body of liquid water that gradually froze over time. As water famously expands when it transitions into ice, the growth of this internal ice would have placed immense stress on the moon's outer crust, potentially causing it to crack and split apart in the intricate patterns we can still discern. Others propose that tidal flexing, which is the constant stretching and squeezing of Dione caused by Saturn's immense gravitational pull, may have generated sufficient heat and stress to create these dramatic features. We still don't have all the definitive answers, but the possibilities are truly captivating. Dione follows an orbit around Saturn at an average distance of about 400 kilometers. It finishes one full circle every 2.7 Earth days. Dione is also gravitationally locked to Saturn, meaning that one particular side of the Moon is always facing the giant planet, much like our own Moon always presents the same face to Earth. This means that from any fixed point on Dione's surface, Saturn would remain motionless in the sky, a vast, ringed spectacle that never shifts its position. This constant orientation has significant consequences for the Moon's surface, affecting how sunlight and radiation interact with different hemispheres. Just like many of the other moons within the vast Saturnian system, Dione takes part in an intricate, synchronized movement of orbital resonances. This cosmic dance has had a profound impact on its long-term evolution. Perhaps the most significant of these orbital relationships is the 201 mean motion resonance that Dione shares with Enceladus, another fascinating moon we'll discuss later. What this actually means is that for every single orbit Dione completes around Saturn, Enceladus precisely finishes 2 orbits. This isn't just a random occurrence. It's a powerful gravitational connection that has locked these 2 moons into a precisely synchronized pattern, one that has distinct effects on both worlds. This specific resonance generates powerful tidal forces that, in turn, create heat within the interiors of both moons. However, these effects are considerably more dramatic on Enceladus, which famously exhibits extraordinary geological activity. This includes its well-known southern polar geysers, which constantly erupt plumes of water ice into the cold vacuum of space. Dione, being a larger body, experiences proportionally less of this tidal heating from the same orbital relationship. Its greater mass and slightly different internal structure mean that while it is warmed by these forces, the energy doesn't manifest in such spectacular, outward displays of activity. The internal flexing still occurs, a constant kneading from Saturn's gravity, but the heat generated is likely distributed differently within Dione's interior, perhaps not reaching the critical temperatures or pressures needed to drive dramatic plume activity at the surface, at least not in the same way we see on Enceladus. Did you know that Dione also has its own small companions? There are 2 tiny moons, named Helene and Polydeuces, that orbit Saturn at precisely the same distance as Dione. These miniature satellites occupy what are known as Lagrange points within Dion's orbit. These are stable gravitational positions, like cosmic parking spots, that either precede or follow Dion as it makes its way around Saturn. Helene is situated at Dion's leading Lagrange point L4, while Polydeuces trails behind at the L5 point. These small bodies, sometimes referred to as Trojan moons, are only a few kilometers across. They are most likely either captured objects, drawn in by Saturn's gravity and Dion's influence, or they might have formed from accumulated debris in Dion's orbital path early in the system's history. Their presence highlights the complex gravitational ballet happening throughout the Saturnian system, where even tiny fragments can find stable niches within the orbits of larger bodies. But let's return to that intriguing question. What about a possible subsurface ocean within Dione? The mere possibility is certainly captivating, especially for scientists who are always intensely interested in any location within our solar system that might harbor liquid water. This is because all oceans, wherever they are found, hold the potential to be environments where life could emerge. So, the existence of an ocean on Dione would be a truly significant discovery, and this idea isn't without some supporting evidence. Cassini's magnetometer, a scientific instrument designed to measure magnetic fields, detected a faint interaction between Dione and Saturn's vast magnetosphere. Some scientists interpret this subtle magnetic signature as evidence for a conductive layer situated beneath Dion's icy surface. This conductive layer could very well be a salty subsurface ocean. The extensive systems of fractures visible across Dion's surface also strongly hint at significant geological activity in its past, processes that could have been driven by the presence of liquid water deep below. Furthermore, scientific models of Dion's internal heat budget, which take into account heat generated both by radioactive decay within its rocky core and by the tidal heating from its orbital resonance with Enceladus, suggest that Dione may have produced enough internal warmth throughout its history to sustain a liquid layer. This would be a stable body of liquid water nestled between its rocky core and its thick, icy outer crust. If Dione indeed harbors a subsurface ocean, it would add another name to the growing list of ocean worlds in our solar system. These include places like Jupiter's moon Europa, Saturn's own Enceladus, and potentially even its largest moon, Titan. Such worlds could conceivably provide habitable environments for simple forms of life, pushing the boundaries of where we once thought life could exist beyond Earth. However, there's a key distinction. Unlike Enceladus, which dramatically spews plumes of water vapor into space, Dione currently shows no obvious signs of geological activity that would offer easy access to any subsurface ocean. If an ocean truly exists within Dione, it remains deeply hidden, lying kilometers beneath a thick, frozen exterior, waiting to be discovered. Since the Cassini mission concluded in 2017, when the spacecraft was intentionally sent plunging into Saturn's dense atmosphere, no other spacecraft has returned to visit the Saturnian system. This means that our current understanding of Dione relies entirely on the data gathered during those limited, but incredibly valuable, encounters with both Cassini and the earlier Voyager probes. Despite this, the scientific community has put forward several intriguing concepts for future missions to the Saturn system, many of which would include further, more detailed exploration of Dione. These proposals include dedicated orbiter missions designed to study multiple moons of Saturn in depth. There are also concepts for landers that could potentially touch down directly on Dion's surface, offering unprecedented close-up observations. Even more specialized missions have been envisioned, specifically designed to search for definitive signs of a subsurface ocean. One particularly ambitious idea is the Enceladus Orbiter, a mission that would primarily focus its attention on Enceladus, but which could also make multiple flybys of Dione. Another proposed mission, aptly named Journey to Enceladus and Titan, would similarly concentrate on those two prominent moons. Yet it would also include valuable observations of Saturn's other major satellites, Dione among them. While none of these exciting mission concepts have yet received official approval for development, the profound scientific questions raised by our limited exploration of Dione ensure that it remains a highly compelling target for future study. Its veiled potential for a hidden ocean and its complex geological history make it a prime candidate for continued investigation. As we step back from our close examination of Dione, we are left with a compelling image of a world full of fascinating contrasts. It's a moon whose seemingly static, icy surface actually tells a dynamic story of a tumultuous past. The extensive networks of bright fractures that crisscross its face speak to powerful forces that have both shaped and reshaped this world over countless eons. The striking difference between its heavily cratered trailing hemisphere and its smoother leading face hints at ongoing processes that continue to sculpt its features. And those subtle clues embedded within its gravitational and magnetic signatures whisper the tantalizing possibility of a vast, hidden ocean lying beneath its frozen exterior. In many ways, Dione perfectly illustrates the surprising complexity we have gradually uncovered throughout Saturn's extensive system of moons. What once appeared as nothing more than distant points of light in our early telescopes have been revealed as truly unique worlds, each with its own distinct geological character and its own intricate evolutionary history. These incredible discoveries challenge us to completely rethink our understanding of what drives geological activity in the far reaches of the outer solar system, where the sun's warmth is simply too faint and distant to power the kinds of processes we typically observe here on Earth. Within the grand, silent symphony of Saturn's many moons, Dione plays its own distinct melody. It's a tune that continues to captivate and inspire us, urging us to look ever deeper into the profound mysteries of our vast solar system. Now, let's consider a different kind of mystery, one that truly embodies the unexpected. Can a moon simply vanish? It turns out that it is indeed possible. In the very early days of telescopic astronomy, the Saturnian moon Iapetus would routinely appear to disappear from sight entirely. Some nights, it would be clearly visible, and then, on other nights, it would be completely gone. This was the ultimate cosmic disappearing act, a true magician's trick on a planetary scale. But as we slowly began to understand how this trick was performed, the mysteries surrounding Iapetus only grew deeper. That's because Iapetus is a place of profound and almost unbelievable contrast. One entire half of this moon is plunged into near absolute darkness, while the other half gleams with the dazzling brilliance of reflective ice. Adding to its strangeness, around its equator, there stands a colossal mountain range, a stony girdle wrapped precisely around its middle, whose very origins continue to defy all easy explanation. Why does this moon exhibit such a dramatic, two-faced characteristic? What cataclysmic event, or perhaps what slow, inexorable process, could have carved out a mountain chain taller than Mount Everest in such an enigmatic location? And what profound secrets does this distant, peculiar world hold about the turbulent, youthful period of our solar system's formation? We're about to find out. Let's begin the story of Iapetus with the sharp observations of Giovanni Domenico Cassini. In 1671, using the advanced refracting telescopes available at the Paris Observatory, Cassini noticed a new speck of light orbiting the majestic, ringed giant. But this newly discovered moon behaved in a very peculiar way. When it was positioned on the western side of Saturn during its orbit, it was reasonably easy to spot. However, as it traveled to the eastern side, it seemed to fade dramatically, becoming incredibly faint, often disappearing entirely from view even in those powerful telescopes. Reflecting on his detailed observations, Cassini himself noted that sometimes, after it had begun to disappear with the 32-foot telescope, it was sought in vain the very next day with an even larger 45-foot telescope. Cassini, with remarkable insight, concluded that this moon must possess one hemisphere that is significantly darker than the other. He also deduced that it must be tidally locked to Saturn, meaning it always kept the same face towards its parent planet, just as our own moon consistently shows the same face towards Earth. This arrangement meant that as Iapetus orbited Saturn, it would alternate between presenting its bright face and its dark face towards our vantage point on Earth. When the bright side faced us, as it did on the western side of its orbit, it was clearly visible. But when the dark side was turned towards us, on the eastern side, it simply faded from view. This was an astonishing observation for the 17th century, representing the very first time a surface property had been detected on a planetary moon beyond our own Earth moon system. Cassini initially named the 4 moons he discovered Sidera Laodicea, or the stars of Louis, in honor of King Louis XIV. However, these names didn't endure. Later, in the 19th century, John Herschel proposed using names drawn from the Titans of Greek mythology, the brothers and sisters of Saturn or Cronus, the Titans' king. So, Iapetus, who was the father of Atlas and Prometheus, and by extension, the mythological father of Prometheus's creations, humankind, became the fitting moniker for this peculiar world. For centuries after its discovery, Iapetus remained little more than that perplexing point of light, consistently exhibiting its bizarre brightness variations. Even the Voyager probes, which completely transformed our understanding of the outer solar system in the late 1970s and early 1980s, only managed distant flybys. Voyager 1 did capture images that clearly showed the stark dark, bright difference, definitively confirming Cassini's original deduction. However, the resolution of these early images wasn't high enough to reveal intricate surface details. Voyager 2 had a slightly better chance, passing closer and offering us our first tantalizing hint of another astonishing feature, a subtle suggestion of a massive ridge near the moon's equator. But the complete picture, the truly breathtaking strangeness of Iapetus, would have to wait for the arrival of a spacecraft specifically dedicated to exploring Saturn and its system. Then, the Cassini spacecraft arrived, named so fittingly after the moon's original discoverer. Reaching Saturn in 2004, the Cassini mission would embark on a 13-year journey, gradually unveiling the many secrets of the ringed planet and its incredibly diverse family of moons. And Iapetus was certainly high on its list of priority targets. Cassini's observations, particularly a close, targeted flyby in September of 2007, which brought the probe within a mere 640 kilometers of Iapetus's surface, completely transformed our view of this moon. From a distant, puzzling glint, it became a complex world that we could finally study in detail. Iapetus is a moon characterized by a remarkably low density, only about 1.22 times the density of liquid water. This suggests that its composition is primarily water ice, possibly as much as 75%. Its shape isn't perfectly spherical, partly due to the presence of that strange equatorial ridge, which gives it a distinctive, somewhat flattened, walnut-like appearance. It's not believed to possess a subsurface ocean like Enceladus or Europa, as there's no compelling evidence of recent geological activity or the intense tidal heating that would be needed to maintain liquid water deep beneath its icy shell. Its surface is ancient, incredibly cold, and heavily marked by craters, particularly in the brighter regions known as Roncesvalles Terra, a testament to billions of years of constant bombardment from space. Its orbit is also quite unusual when compared to other Saturnian moons. Iapetus travels much farther out, at an average distance of about 3.5 million kilometers. This is more than twice the distance of the next major moon, Titan. This significant distance means it takes a long time, 79.3 Earth days, to complete just one orbit around Saturn. Crucially, its orbital path is also slightly inclined, tilted by approximately 15 degrees relative to Saturn's equatorial plane, which is where most other major moons orbit. This greater distance means Apetus is less influenced by Saturn's powerful magnetosphere and the intense radiation belts that are closer to the planet. Its inclined orbit might offer a clue to its formation or its early migration history, possibly indicating that it didn't form within the same equatorial disk as Saturn's closer, more regular moons. But now, let's focus on the aspect of Iapetus that makes it so utterly captivating to observe its unique surface. This surface is cleanly divided into two incredibly distinct regions. The leading hemisphere, which is the side that faces forward as Iapetus moves along its orbit around Saturn, is unbelievably dark. This region is known as Cassini Regio, and it covers roughly 40% of Iapetus's entire surface. Its albedo, which is a measurement of how much light it reflects, is extremely low, falling somewhere between 0.03 and 0.05. To put that into perspective, it's as dark as asphalt or finely crushed coal dust. This means it absorbs almost all of the sunlight that falls upon it, making it appear almost black in space. In stark contrast, the trailing hemisphere, which is the side facing away from the direction of its orbit, along with the polar regions, is astonishingly bright. This area, which includes Roncesvalles Terra to the north and Saragossa Terra to the south, boasts an albedo of 0.5 to 0.6. That means it is 6 times as bright as freshly fallen snow or pristine water ice. This almost tenfold difference in albedo represents the greatest hemispheric albedo contrast known anywhere else in our entire solar system. Imagine seeing this world up close, one side a deep, reddish, brown or jet black, the other a dazzling, brilliant white. In some areas, particularly near the equator, the boundary between these two halves can appear remarkably sharp, almost as if it were painted on with a precise line. In other regions, especially at higher latitudes, the transition is more gradual. Here, bright, impact-scarred craters are scattered across the dark terrain, and dark streaks subtly dust the bright terrain, looking almost like splashes of mud on snow. Images from Cassini vividly capture this incredible contrast. It is, quite literally, a world split down the middle. So, what exactly causes this striking yin-yang appearance? For a long time, the leading scientific theory proposed an internal origin. Perhaps some form of dark cryovolcanic material erupted from Iapetus's interior, then coated only one side of the moon. A paper that reviewed the Voyager data, published by Bradford Smith and his colleagues in 1981, argued for this theory. They identified a ring-shaped feature, interpreted as a crater partially flooded with dark eruptive material, as supporting evidence. However, Cassini's advanced radar and imaging data later revealed that this dark material forms a relatively thin layer, perhaps only tens of centimeters to a meter thick in most places. Furthermore, impact craters within Cassini Regio often excavate bright, icy material from underneath, effectively punching through the dark veneer. This strong evidence suggested that the dark substance wasn't welling up from below, but was instead being deposited onto the surface from above. A paper published in 1982 presented spectrophotometric observations of the dark leading surface, finding that the material's composition was carbonaceous, meaning it contained carbon compounds. This was found to be similar to the Murchison CM2 meteorite, which fell to Earth during a meteor shower in 1969. To explain this intriguing finding, the authors looked to potential culprits much closer to Iapetus, within the broader Saturn system itself. The prime suspect that emerged was dust originating from Saturn's outer, irregular moon Phoebe. Phoebe is a relatively large, dark moon that was captured by Saturn's gravity. It orbits the planet in the wrong direction, meaning it follows a retrograde orbit, and it does so at a significant distance from Saturn. Over billions of years, countless impacts on Phoebe and other small, dark, retrograde, orbiting moons have kicked up an immense, diffuse ring of dark dust particles. The Sun's radiation then exerts a subtle but constant pressure on these dust particles. This phenomenon is known as the Poynting-Robertson effect. As a result of this effect, this dust slowly spirals inwards towards Saturn, also moving in a retrograde direction. Now, let's bring this back to Iapetus. It orbits Saturn in a prograde direction, which is the same direction as Saturn's rotation and that of most other major moons. However, its orbit is significantly farther out than the main rings and the closer moons. As Iapetus journeys around Saturn, its leading hemisphere essentially plows head on into this incoming stream of retrograde dark particles, which originate largely from the Phoebe group. It's very much like driving a car through a dense swarm of insects. They mostly splatter on your front windshield. The trailing hemisphere, shielded by the moon itself, collects far less of this dark material. However, simple deposition alone doesn't completely explain the sheer intensity of the darkness we observe on Iapetus's leading side, nor does it account for the intricate complexity of the border between the dark and bright regions. This is where the fascinating processes of thermal segregation and water-ice sublimation come into play. The dark material, once deposited on the leading hemisphere, absorbs much more sunlight compared to the surrounding bright ice. This absorption causes the surface temperature in those dark areas to rise, even if only slightly. Iapetus is an incredibly cold world, but even a small temperature increase is sufficient to cause the volatile water ice to sublimate. This means it transforms directly from solid ice into water vapor gas, completely bypassing the liquid phase. This sublimating water vapor doesn't simply vanish into space because Iapetus rotates very slowly. Its day is approximately 79 Earth days long, precisely matching its orbital period. During this prolonged daytime, temperatures are higher, and the ice has ample time to sublimate away from the warmer, dark areas. In fact, sublimation on Iapetus is quite efficient. If its surface were pure ice, we would see over 100 meters of ice lost to sublimation over 1 billion years. But where does this ice go? It preferentially recondenses and freezes onto the coldest available surfaces. These are the already bright, icy regions on the trailing hemisphere and near the poles, which reflect more sunlight and thus remain significantly cooler. Scientists suggest that due to its negligible atmosphere, these sublimating water molecules follow ballistic trajectories, essentially jumping impressive distances across the moon's surface to the colder trailing hemisphere, almost like tiny missiles. This process creates a runaway positive feedback loop. Dark areas, once slightly warmed, lose their ice and become even darker as the underlying dark dust concentrates. They then absorb even more heat, leading to further sublimation of ice. Conversely, bright areas remain cold, actively collect this migrating frost, and become even brighter. This increased brightness reflects more sunlight, keeping them even colder, which in turn allows them to collect even more frost. Over millions and billions of years, this powerful process has dramatically sharpened the boundary between the incredibly dark leading hemisphere and the dazzlingly bright trailing hemisphere, ultimately leading to the extreme contrast we observe today. So, this great dichotomy on Iapetus appears to be a sophisticated combination of external pollution from retrograde, orbiting moons, and an internal sorting mechanism powerfully driven by sunlight and the sublimation of water ice. It's a truly remarkable example of intricate planetary processes at work on a grand scale. Yet, the striking two-tone coloration is only one part of Iapetus's profound strangeness. As Voyager 2 subtly hinted at, and as Cassini later confirmed in stunning detail, Iapetus possesses another unique geological feature, one unparalleled in our known solar system, a colossal equatorial ridge. This remarkable ridge is, in essence, a towering wall of mountains, stretching for approximately 600 kilometers, extending at least halfway around the Moon's entire circumference. On average, it measures about 200 kilometers wide at its base and reaches astonishing heights of up to 20 kilometers above the surrounding terrain. To put that into perspective, that's significantly taller than Earth's Mount Everest. And perhaps the most baffling aspect is that it follows the Moon's equator almost perfectly, primarily confined within the dark Cassini Regio, although more equatorial mountains, identified by Voyager on the trailing hemisphere, could potentially be a continuation of this vast structure. In images captured by Cassini during its close flyby, the sheer scale of this feature is absolutely breathtaking. It gives Iapetus a very distinct, almost walnut-like shape. What could possibly have formed this massive belt of mountains? This remains one of the biggest ongoing mysteries surrounding Iapetus. Several hypotheses have been proposed, each with its own merits and drawbacks. One prominent idea suggests that the ridge is a remnant, a fossilized relic, of a much faster spinning past. Recent scientific models have indicated that early in its history, perhaps shortly after its formation, Iapetus might have been rotating at a significantly higher speed, possibly completing a full rotation in around 16 hours. This rapid spin would have dramatically increased its ablateness, causing the Moon's equatorial regions to bulge outwards due to strong centrifugal force. This would have happened while the Moon was still young and relatively pliable, perhaps even partially molten. As Iapetus gradually cooled and solidified, this equatorial bulge would have frozen permanently in place. Later, powerful gravitational interactions with Saturn slowly decelerated the Moon's rotation over millions of years, until it became tidally locked, rotating only once per orbit, which is about every 79 Earth days. As its rotation slowed, the centrifugal force that had supported the bulge diminished, and the now solid crust couldn't fully relax back into a perfect spherical shape. The material essentially slumped downwards, piling up near the equator to form the massive ridge we observe today. This theory fits well with the ridge's precise equatorial location and its ancient, heavily cratered appearance, suggesting it formed very early in Iapetus's history. However, it does require Iapetus to have spun incredibly fast, possibly quite close to its structural breakup speed, and to have solidified while successfully maintaining that pronounced bulge. Another intriguing hypothesis proposes that the ridge is the result of material falling onto Iapetus from an external source. Specifically, this theory points to the collapse of a subsatellite, a smaller moon, or even a ring system that once orbited Iapetus itself. If Iapetus possessed its own debris ring early in its history, perhaps sourced from a captured body or from a massive impact event, this material would naturally have orbited above its equator. If this ring then became unstable, or if Iapetus itself migrated slightly in its orbit, the ring material might have been pushed just beyond the Roche limit. The Roche limit is the critical point at which the powerful tidal effects of a larger body overcome the internal gravity holding a smaller body together. This might have caused the ring material to slowly rain down onto Iapetus's surface, preferentially accumulating along the equator. This could potentially explain why the ridge seems most prominent on the dark leading hemisphere, if the ring material itself was dark, or if its deposition happened to coincide with the influx of dark dust from Phoebe. Some models suggest that even the breakup of a relatively small moonlet within Iapetus's Roche limit could provide enough material to form such a feature. While elegant in explaining the location, the exact mechanisms for forming and then collapsing such a ring are still subjects of intense scientific debate. Other theories, such as those involving tectonic processes or convective upwelling from the Moon's interior, struggle to adequately explain why the geological activity would be so narrowly confined to the equator over such an immense distance. Similarly, a single, giant impact event is highly unlikely to produce a long, linear, and perfectly equatorial feature like the ridge. Cassini's incredibly detailed images clearly show that the ridge is heavily cratered, further confirming its ancient origins. It appears to be structurally composed of icy, crustal material. Some sections also show clear evidence of landslides and collapse features, hinting at its long and complex geological life. Whatever the exact process, it must have occurred very early in Apetus's history, perhaps within the first few 100 million years of the solar system's formation. The ridge stands as a monumental reminder of Apetus's dynamic youth, a frozen record of ancient processes that we are still striving to fully comprehend. So, what do we truly know about Iapetus today? We certainly know far more than we once did, but still considerably less than we would like to. The Cassini mission fundamentally altered our perception of this truly fascinating moon. Its close flyby provided the crucial data that solidified the theory involving exogenic dust and sublimation as the primary explanation for the moon's striking two-faced appearance. It also gave us astonishing, high-resolution views of the colossal equatorial ridge, enabling detailed study of its complex structure and morphology, even if its ultimate origin remains a topic of spirited debate. Cassini meticulously measured Iapetus's precise shape, its gravitational field, and its surface composition with unprecedented accuracy. Without Cassini, Iapetus would have largely remained the faint, perplexing point of light it had been for centuries. And yet, despite all these advancements, so many mysteries persist. What is the true, definitive origin of Iapetus's enigmatic ridge? What is the dark material on Iapetus's mysterious leading face actually composed of, beyond simply being, carbonaceous? Unless we send another mission there, a dedicated explorer designed to study this specific world up close, it will be incredibly difficult to know for sure. Unfortunately, no missions are currently planned to either sample or even orbit this perplexing place. So, for now, we largely remain in the dark, which, in a way, feels quite appropriate. After all, as we mentioned at the very beginning, Iapetus was once the solar system's ultimate vanishing act, and a true magician, as they say, never fully reveals all their secrets. Now, let's shift our focus to another remarkable world within the vast expanse of our solar system, one that also orbits the majestic ringed giant, Saturn. This is Rhea, Saturn's second largest moon. While you are probably more familiar with its enormous sibling, Titan, Rhea is a truly fascinating place in its own right, harboring many secrets and wonders that are just as compelling. It boasts towering ice cliffs, hundreds of meters high, and an internal structure that continues to challenge conventional scientific models. There's also an enigmatic discovery that lingers around this moon, a finding that's equally as strange as something significant we didn't find there. It's time for this often overlooked moon to step out from the shadow of its larger sibling. Let's explore everything there is to know about Rhea. Rhea was discovered on December 23, 1672 by Giovanni Domenico Cassini, the same Italian astronomer who made so many crucial contributions to our understanding of Saturn and its many moons. Named after the Titan goddess Rhea from Greek mythology, this moon has been a subject of intense fascination for astronomers and planetary scientists for centuries. Let's start with some basic facts. Rhea is the second largest moon of Saturn, second only to the mammoth Titan, with a diameter of 528 kilometers. To give you a sense of scale, it's roughly half the size of our own moon. If we could somehow place Rhea next to Earth, its diameter would stretch from London all the way to Warsaw. Rhea orbits Saturn at a distance of approximately 527,000 kilometers, completing one full orbit every 4.5 Earth days. It is gravitationally locked in a synchronous rotation with Saturn, meaning that the same side of Rhea always faces the planet. This is a common characteristic among many of the large moons found throughout our solar system. The surface of Rhea is one of the most reflective surfaces we know of in our entire solar system, with an albedo of 0.7. This means that it reflects an astonishing 70% of the sunlight that strikes it, making it appear dazzlingly bright white against the deep black backdrop of space. This exceptionally high reflectivity is due to its primary composition. Rhea's surface is predominantly made of water ice. However, this doesn't mean it's a featureless sheet of ice. Far from it, actually. The Moon's surface is heavily marked by craters, which tell a vivid story of countless ancient impacts and a long, often violent history. The largest of these impact craters, named Mamaldi, spans an impressive 480 kilometers in diameter. To give you another comparison, that's roughly the distance from Paris to Amsterdam. These craters aren't just simple scars on Rhea's surface. They are like windows into the Moon's deep past and its underlying composition. Observations have shown that the bottoms of some craters appear noticeably darker than the surrounding terrain. This could indicate that impacts have excavated material from beneath Rhea's bright surface, possibly exposing darker, amorphous water ice or material that was melted and then refrozen during the impact. In certain photographs, you can clearly see a crater in Rhea's southern hemisphere, surrounded by a hollow of bright, ejected material. But one of the most intriguing features of Rhea is its system of bright, wispy streaks that crisscross its surface. These delicate-looking patterns were first observed in detail by the Voyager space probes in the early 1980s. However, their true nature wasn't fully understood until the Cassini mission provided incredibly high-resolution images decades later. Initially, scientists thought these wisps might be simple deposits of frost or ice. But Cassini's detailed observations revealed them to be something far more dramatic. Towering ice cliffs, some hundreds of meters high. These are most likely the result of past tectonic activity within Rhea, where the icy crust fractured and some sections were thrust upwards, creating these elevated scarps. These features offer us crucial clues about the Moon's geological history and the complex processes that have shaped its surface over billions of years. Yet, Rhea's mysteries don't stop at its surface. In 2010, data collected from the Cassini spacecraft led to a surprising announcement. Rhea appeared to possess a tenuous atmosphere, or exosphere. While a small amount of gas around Rhea might have been expected, it was truly unexpected that there was enough to be measurable. The detected atmosphere primarily consisted of oxygen and carbon dioxide. The oxygen, however, was incredibly thin, about 5 trillion times less dense than Earth's atmosphere at sea level. While extraordinarily thin, the mere presence of this atmosphere sparked intriguing questions about its origin and how it could be sustained. One prevailing theory suggests that the oxygen is produced by the decomposition of water ice on Rhea's surface when it's struck by ions emanating from Saturn's powerful magnetosphere. The carbon dioxide, on the other hand, is thought to be the result of organic molecules on the surface being oxidized by the newly formed oxygen in the exosphere. This remarkable discovery made Rhea the very first moon known to have an oxygen atmosphere, aside from Jupiter's much larger moons Ganymede and Europa. It also opened up entirely new avenues for research into the complex interactions between Saturn's numerous moons and the planet's vast, powerful magnetosphere. Rhea's exterior is certainly fascinating, but what about its interior? Let's delve deeper, quite literally. While we can't directly observe what lies beneath Rhea's thick, icy surface, scientists have employed various methods to infer its internal structure, based on Rhea's average density of 1.236 grams per cubic centimeter. which is only slightly higher than that of pure water, we can deduce that Rhea is composed primarily of water ice, making up about 75% of its mass, and a smaller fraction of rocky material, accounting for the remaining 25%. This composition often leads to Rhea being described as a frozen dirty snowball, a description that accurately captures its internal makeup. This places Rhea in stark contrast to moons like our own, which are primarily solid rocky bodies. When the Cassini spacecraft visited Rhea, its sophisticated instruments also provided incredibly valuable data about the moon's surface composition. Spectroscopic observations, which analyzed the light reflected from the surface, confirmed that water ice is indeed the dominant component of Rhea's exterior. However, these observations also detected the distinct presence of other materials. One particularly surprising discovery was the identification of carbon dioxide trapped within the surface ice. This finding suggests that Rhea's ice isn't simply pure water, it actually contains other compounds, potentially including more complex organic molecules. Due to its higher moment of inertia, a measure of how mass is distributed within a rotating body, most scientists currently believe that Rhea is not fully differentiated into distinct layers, at least not in the same way more massive bodies are. Instead, it is generally thought to be a more homogeneous mix throughout its interior, with the notable exception of its central core. However, some scientists have challenged this model. In 2006, a research paper published in the journal Icarus put forward the intriguing idea that Rhea might actually possess a layer of liquid water beneath its surface, a hidden subsurface ocean. While this concept remains highly speculative and isn't as strongly supported as the evidence for subsurface oceans on moons like Europa or Enceladus, it represents a truly fascinating possibility. Future missions could potentially investigate this further. The confirmed presence of such an ocean would have profound implications for Rhea's potential to host life, and for our broader understanding of the conditions necessary for liquid water to exist in the frigid outer reaches of our solar system. Rhea's interior certainly holds its share of mysteries, but one of the more puzzling features of Rhea is its overall shape. While many large moons and planets tend towards a perfect sphere due to the powerful pull of their own gravity, Rhea is noticeably not perfectly round. It's slightly flattened at its poles and bulges out at its equator, a shape that scientists refer to as a triaxial ellipsoid. What's particularly strange is that Rhea's observed shape doesn't quite align with what we would expect based solely on its current rotation rate. This discrepancy has led scientists to propose that Rhea might possess a non-uniform internal structure, perhaps with denser material concentrated in certain areas away from its exact center. Now, let's talk about one of the most exciting periods in Rhea's recent observational history, the close flybies conducted by the Cassini mission. The Cassini spacecraft, a collaborative project involving NASA, ESA, the European Space Agency, and the Italian Space Agency, dedicated over a decade to meticulously studying the entire Saturnian system. This extensive work included several incredibly close encounters with Rhea. The closest of these flybies took place on January 11, 2011, with Cassini passing a mere 76 kilometers above Rhea's surface. The final close flyby occurred on March 9, 2013, when Cassini passed just 997 kilometers above Rhea's surface. These close approaches allowed the spacecraft to capture unbelievably detailed images of Rhea's cratered terrain and to gather a wealth of valuable data about the moon's composition. Crucially, these flybys also helped determine that Rhea does not possess an internal magnetic field of its own. These close observations provided us with our very best look yet at Rhea's surface features. They revealed a landscape dominated by two primary types of terrain: heavily cratered regions and younger, much smoother plains, a distinction first hinted at by the earlier Voyager missions. The heavily cratered areas we discussed earlier are believed to be extremely old, possibly dating back to the very early days of the solar system's formation. These ancient surfaces act as a frozen record of the intense bombardment that characterized the solar system's turbulent youth. The smoother plains, on the other hand, are likely the result of more recent resurfacing events, perhaps caused by material ejected from exceptionally large impact events. This ejected material would have subsequently fallen back to the surface, effectively filling in older craters and creating the smoother regions we see today. But perhaps one of the most intriguing results from the Cassini mission was actually what it didn't find. Prior to Cassini's arrival in the Saturn system, some scientists had put forward the hypothesis that Rhea might possess its own system of rings. This idea was based on some unusual measurements of electron densities detected around Rhea by Cassini in 2005. However, despite conducting careful and deliberate searches during its many flybys, Cassini found no definitive evidence of rings orbiting Rhea. This non-detection doesn't completely rule out the possibility of some kind of tenuous debris disk around Rhea, but it certainly makes it much less likely than originally thought. Another fascinating aspect of Rhea is its specific location within Saturn's incredibly complex system of moons. Rhea orbits Saturn within what is known as the E-ring, a very diffuse ring composed of tiny ice particles. This E-ring is thought to be continuously replenished by the cryovolcanic eruptions emanating from Enceladus, another one of Saturn's icy moons. While Rhea itself doesn't appear to be geologically active in the same spectacular way as Enceladus, its position within this ring means it is constantly interacting with these microscopic ice particles. Although Rhea is situated at the very extremities of the E-ring, beyond where the ring is densest, this constant interaction over long periods of time could potentially affect Rhea's surface properties, and might even contribute to the moon's remarkably bright appearance. As we reflect on all that we've learned about Rhea, it becomes clear that this moon, often overshadowed by its more famous siblings, is a genuinely fascinating world in its own right. From its heavily cratered hemispheres to its relatively smooth plains, from its incredibly tenuous atmosphere to its unique place within Saturn's intricate system of moons, Rhea continues to intrigue scientists and spark our collective imagination. But our exploration of Rhea is far from complete. Many fundamental questions still remain unanswered. What is the precise nature of its internal structure? How has it evolved over the billions of years since its formation? And could it possibly harbor simple forms of life within a hypothetical subsurface ocean? These questions, and many more, eagerly await future missions to the Saturnian system. While there are currently no planned missions specifically targeting Rhea, it is highly probable that the moon will be observed by any future spacecraft sent to study Saturn and its diverse family of moons. As we bring our journey to Rhea to a close, let's take a moment to truly appreciate the incredible diversity of worlds that exist within our vast solar system, from the scorching, cloud-shrouded surface of Venus to the frigid, icy plains of distant Pluto, from the towering, ancient volcanoes of Mars to the potential subsurface oceans of icy moons like Enceladus. Our cosmic neighborhood is absolutely filled with wonders, all patiently waiting to be explored. Rhea, with its brilliantly icy surface reflecting the faint, distant sunlight, stands as a powerful testament to the inherent beauty and enduring mystery of our universe. As we continue to explore and learn, who knows what other secrets this distant, quiet moon may yet reveal to us. You might not know much about Tethys, but there's one crucial thing you should understand about it. The moon called Tethys is an absolute survivor. It's an icy world orbiting Saturn at a distance of 295 Zalozan kilometers. At first glance, it might appear somewhat unremarkable, a relatively plain sphere of ice. However, Once you learn what this moon has endured, you'll be astonished that it's even still here at all. Just take a closer look at its deeply scarred surface, and you'll immediately see what I mean. Not many moons in our solar system possess a gargantuan trench system that wraps around 3/4 of their entire body. A tectonic rupture so vast it almost defies belief for a world of this modest size. And directly opposing this immense chasm, a gigantic impact basin stares back at us, clear evidence of a collision so incredibly violent that, by all rights, it should have shattered this moon into countless fragments. What powerful forces could have caused such immense scaring? And how did Saturn's fifth largest moon manage to survive such an overwhelming onslaught? The answers to these questions lie hidden within its frozen, icy shell, and today, those answers are slowly but surely coming to light. The first observation of Tethys also came from Giovanni Domenico Cassini. Following his arrival and extensive work at the Paris Observatory, Cassini, the very man who, centuries later, would have a famous spacecraft named in his honor, identified Tethys in 1684 alongside Dione. He added these two to his growing tally of Saturnian moons, which already included Rhea and Iapetus. Following their discovery, these moons were initially given the collective name Sidera Ludoicea, or the Stars of Louis, in tribute to King Louis XIV. However, as with Iapetus, these names didn't last. In the 19th century, John Herschel again proposed a new naming convention, drawing upon the figures of the Greek Titans to align with Saturn, who was known as Cronus, the king of the Titans. Tethys, quite fittingly for a world composed primarily of water ice, was named after a Titaness and a sea goddess. And it is indeed a profoundly icy world. A key characteristic of Tethys, one that was clearly revealed by gravitational measurements, primarily collected by the Cassini spacecraft, is its remarkably low density. This density is approximately 0.97 grams per cubic centimeter, which is just 0.97 times the density of liquid water. As a direct consequence of this extremely low density, Tethys's total mass is less than 1% of that of our own moon, despite spanning about 1/3 of its diameter. This exceptionally low value very strongly indicates that Tethys is composed almost entirely of water ice, with only a very small amount of rocky material integrated within its structure. This composition suggests that Tethys most likely never fully differentiated into a distinct rocky core and a separate icy mantle. Or, if it did, that rocky core is exceptionally tiny. The low density might also imply some degree of internal porosity, meaning the ice within its interior might not be perfectly compacted, potentially containing voids or less dense ice structures. This specific composition makes Tethys a quintessential example of an outer solar system ice world. Physically, Tethys presents itself as a typically bright, icy satellite. Its high bond albedo, which indicates that it reflects around 60% of the incident radiation from the Sun, confirms a surface that is largely dominated by water ice. This ice is relatively free from significant amounts of darker, rocky, or carbonaceous contaminants, materials that are more commonly seen on moons like Iapetus or Phoebe. Tethys also possesses an irregular shape, a result of the complex gravitational influences exerted by its neighbors and by Saturn itself. Its classical spherical shape has been subtly squashed into what is called a triaxial ellipsoid, meaning it has three slightly different axes. However, perhaps the most arresting and dramatic feature on Tethys is one of its colossal landmarks, Ithaca Chasma. This enormous canyon system utterly dominates the moon's topography. It measures an astounding 2,000 kilometers long, approximately 100 kilometers wide, and up to 5 kilometers deep. Now, I really want you to take a moment to truly grasp the immense scale of this feature. Imagine a crack in the earth running from New York City, almost all the way to Denver, Colorado, and you begin to comprehend its size relative to the moon itself. It absolutely dwarfs Earth's Grand Canyon and is proportionally one of the largest canyon systems in the entire solar system, rivaled perhaps only by Valles Marineris on Mars. The very existence of such an imposing feature on what appears to be a relatively simple icy moon immediately begs the question: how on earth did it form? Several theories have been proposed, but the leading hypothesis connects Ithaca Chasma directly to Tethys's internal evolution, suggesting that it may have formed very early in the moon's geological history. As Tethys initially formed and subsequently began to cool, any liquid water within its interior would have started to freeze. And unlike most substances, water famously expands when it freezes. If Tethys once possessed a substantial subsurface ocean, or even just a partially liquid interior, the gradual solidification of this water would have caused the moon's volume to increase, much like an inflating balloon. This internal expansion would have placed immense stress on the moon's rigid outer icy crust. Ithaca Chasma, according to this theory, is the dramatic result of the crust cracking and splitting apart under this relentless internal pressure. It's essentially a global, scale stretch mark, signifying the moon slowly freezing solid from the inside out. The sheer scale of the chasma suggests that Tethys might have expanded laterally by around 5% during this process, which is truly mind-boggling to consider. An entire moon swelling up until it literally began to burst. Other theories have explored potential links to the giant impact crater Odysseus, suggesting that the shock waves from that massive collision might have somehow fractured the opposite hemisphere of the moon. However, Ithaca Chasma is generally believed to be older than the Odysseus Basin, and detailed scientific modeling suggests that the expansion freezing model provides a much better fit for the observed geology. Therefore, Ithaca Chasma isn't just a spectacular visual sight, it's a profound record of Tethys's thermal history, a dramatic indicator that this now frozen world may once have undergone immense, growing pains. On a truly cosmic scale, surface temperatures on Tethys are incredibly low, averaging around 187 degrees Celsius. These extreme temperatures ensure that water ice remains brittle and stable, resistant to sublimation, turning directly from solid to gas, except over extremely long geological timescales. It's so cold there that the water ice on Tethys often behaves much like solid rock. Tethys completely lacks any detectable atmosphere, leaving its surface directly exposed to the harsh and unforgiving environment of space. This means it's constantly bombarded by micrometeoroid impacts, solar radiation, and charged particles trapped within Saturn's powerful magnetosphere. However, not all of those micrometeoroid impacts were micro. One particular impact was so enormous that it nearly shattered frozen Tethys, much like a bullet piercing a snow globe. It's time to take a closer look at the Odysseus crater. If Ithaca Chasma speaks to powerful internal forces, the Odysseus crater unequivocally screams of external violence. Located on Tethys's leading hemisphere, Odysseus is the moon's largest impact basin, measuring approximately 450 kilometers across. That's more than 2/5 of Tethys's entire diameter. The impact event responsible for creating this enormous feature is thought to have occurred sometime between 400 million and 1 billion years ago, and judging by the sheer size of the crater compared to its moon, if Tethys had been as cold and hard as it is now at the time of the impact, there's a significant chance it would have been completely broken into pieces. But it seems highly likely that the impact occurred when Tethys's interior was still partially molten, or at least slushy, allowing it to absorb and dissipate the immense impact energy far more effectively than a completely solid, brittle body ever could have. It was, in a cosmic sense, an incredibly lucky break for Tethys. Interestingly, Odysseus is remarkably shallow for a crater of its immense diameter. Unlike the sharp, bowl-shaped craters we typically observe on rocky bodies like our own Moon or Mercury, Odysseus is relatively flat, its rim subdued. and its central peak complex largely collapsed. This is definitely not how it would have looked immediately after the impact. This unusual morphology strongly suggests a phenomenon known as viscous relaxation was at play over vast geological timescales. Even solid ice, especially under immense pressure and over long periods, behaves somewhat like a very thick, slow-moving fluid, particularly when topography is significant. The immense depression created by the impact and the uplifted rim would have slowly flowed and slumped under Tethys's own gravity, gradually smoothing out the crater's original profile. The degree of relaxation observed in Odysseus provides further crucial clues about the thermal state and composition of Tethys's crust at the time of the impact and in the eons since. This makes perfect sense. Such a large impact tends to release an enormous amount of energy, and it would seem logical that not everything would remain perfectly icy and rigid. The impact likely resurfaced a significant portion of the surrounding terrain, either completely obliterating older craters or smothering them with its vast amounts of ejected material. So, Tethys has certainly taken some severe hits over the years, both from within its own interior and from external forces. But that's not all there is to discover about this remarkable moon made almost entirely of ice. Another notable discovery from Tethys involved its unusual thermophysical properties, which amusingly tied it to a popular 1980s computer game character. In 2015, Cassini's composite infrared spectrometer made a series of detailed observations of Tethys's daytime anti-Saturn hemisphere over a 9-hour period. This data allowed scientists to confirm an anomaly that had actually been identified earlier, in 2012. The lower latitudes of Tethys's leading hemisphere consistently appeared cooler during the day and warmer at night compared to the surrounding regions. This particular area of Tethys also looked darker in infrared and UV color ratio maps when compared to the rest of the leading hemisphere. Funnily enough, when this temperature pattern was mapped out, it made the moon look exactly like a giant Pac-Man, which gave scientists a good chuckle. And, proving their sense of humor, they officially gave this phenomenon the same name. Still, the Pac-Man heat map on Tethys and a similar one observed on its neighboring moon Mimas clearly needed a scientific explanation. Tethys orbits Saturn at an average distance of about 295 Zalozan kilometers, positioning it as the fifth largest moon within the complex Saturnian system. Its orbital period is relatively short, just under 1.9 Earth days. And, like most of Saturn's major moons, it is tidally locked to the giant planet. Why is this important? Well, this constant gravitational interaction ensures that Tethys perpetually presents the same hemisphere towards Saturn. This effectively divides its surface into a leading hemisphere, which faces the direction of its orbit, and a trailing hemisphere. This tidal locking helps to keep the Pac-Man pattern facing in a consistent direction, which also brings us to the moon's overall coloration. The leading hemisphere, the side facing the direction of orbit, appears to be between 10% to 15% brighter than the trailing hemisphere. Its near-infrared spectrum also suggests that it has more pure water ice on its surface. This distinct pattern is generally attributed to external factors, specifically the constant weathering effect caused by particles from Saturn's E-ring and the plumes erupting from Enceladus. The leading hemisphere is the side that gets most exposed to this bombardment. This weathering effectively sandblasts material onto the surface of the leading hemisphere, material which tends to consist of incredibly tiny, submicron-sized icy particles. Smaller water ice particles are known to reflect more light than larger particles, therefore contributing to the leading hemisphere's higher albedo, making it appear brighter. The trailing hemisphere, conversely, is more heavily bombarded by energetic plasma particles that are trapped within Saturn's immense magnetosphere. This high-energy radiation can cause a process known as sputtering, where surface molecules are ejected. It can also break chemical bonds and implant ions, processes collectively referred to as space weathering. These effects tend to darken and redden icy surfaces over long periods. Contamination by micrometeoroids carrying darker material could also play a role in this darkening. In other words, scientists now believe that Saturn's rings and the activity of Enceladus are partly to blame for feeding the Pac-Man pattern. The differential bombardment from ring particles across the Moon's leading hemisphere modifies its surface in a way that gives certain regions a higher thermal inertia. This means these regions store and release heat more effectively than their surroundings, thereby creating the observed temperature differences. It's a pretty fun and unexpected finding, one that truly makes you realize just how much these moons are shaped by their unique and continuous interactions with Saturn's rings and its broader environment. Tethys may not possess the atmospheric complexity of Titan or the obvious, dramatic present-day geological activity of Enceladus, but it is far from a boring, inert world. It is a celestial body that has been profoundly shaped by extreme events. Its epic story is written in bold, unmistakable strokes across its surface, in the form of the immense Ithaca Chasma and the colossal Odysseus crater. It also stands as an incredible example of how even small worlds and moons are intricately influenced by their wider cosmic neighborhoods. Tethys is undeniably icy, but the subtle variations in its surface texture and color hint at ongoing interactions with the dynamic Saturnian environment. Traveling around Saturn and its rings continuously changes Tethys, and by studying both, we gain a deeper understanding of these complex, dynamic interactions. Sadly, there are currently no new missions specifically planned to visit Tethys, but Tethys has survived far worse fates than being simply unvisited. It has been squeezed and stretched by immense gravitational forces. It has been relentlessly sandblasted with icy dust from the E-ring, and it has been struck from above by forces so powerful they could have shattered it completely. Tethys is unequivocally a survivor, and although its outer crust is composed of ice rather than solid rock, it is unapologetically hardy. It has weathered anything the universe has thrown its way so far and will undoubtedly continue to endure for eons to come. Well, everyone, here it is, your most requested video, all about Titan. And to be fair, I can completely understand the intense curiosity surrounding it. It is, after all, the only moon in our entire solar system with a substantial, dense atmosphere. There's also clear and compelling evidence of stable bodies of liquid on its surface, a truly unique feature beyond Earth. And perhaps best of all, humankind has actually sent a probe to visit its surface. So I'll be able to show you a lot of real photos and video footage taken directly from this incredible world. We're about to explore everything you could possibly want to know about Saturn's biggest moon, Titan. But let's start from the very beginning and provide some essential context for this truly remarkable, planet-like place. Titan is the sixth spherical moon orbiting Saturn, and unlike Jupiter's 4 large Galilean moons in the Saturn system, Titan stands almost completely alone in its immense size. The rest of Saturn's moons are comparatively quite small. To give you some idea of just how big it truly is, Titan's diameter is 50% larger than Earth's own moon, and it is 80% more massive. In fact, it holds the title of the second largest moon in the entire solar system, surpassed only by Jupiter's moon Ganymede. It actually appears slightly bigger than Ganymede if you were to place them directly side by side. But this optical illusion is caused by Titan's thick, hazy atmosphere, which extends its apparent diameter. Even without the atmospheric illusion, Titan's real solid body diameter is still larger than that of the smallest planet, Mercury, though it is only about 40% as massive. Because its density is quite low for its enormous volume, its gravitational pull is reasonably weak, at only 0.1 through Earth gravities, or 135 meters per second squared, which is even less than the gravity on our own moon. Due to Titan's notably low density, it is widely believed that its composition is roughly half water ice and half rocky material. Unlike many other celestial objects of comparable size, it is thought that Titan possesses a differentiated interior. This means it has distinct, separate layers, much like Earth does. And, similar to a lot of other large moons in the outer solar system, one of those crucial layers is believed to be a liquid ocean, a vast body of water mixed with ammonia, situated directly beneath the moon's solid icy crust. This liquid ocean is somewhat comparable to Earth's own magma layer, which lies between our planet's core and its crust. This subsurface liquid on Titan has been kept in its fluid state due to a combination of internal heat, immense pressure, and, to a certain degree, the powerful tidal forces exerted by Saturn. The existence of this internal liquid layer was made much more probable when Cassini, the spacecraft orbiting Saturn, detected extremely low frequency radio waves within Titan's atmosphere. Titan's surface is not known to be a good reflector of low frequency radio waves, but a liquid interior would be, effectively acting as a reflective barrier. Another compelling reason for believing in this subsurface ocean is that surface features on the moon have apparently shifted by up to 30 kilometers since Cassini began its detailed observations. This significant shifting could imply that the surface crust is not rigidly attached to the moon's core, but is instead floating freely on this deep liquid ocean layer. And while there is currently no direct evidence of life on Titan, scientists do speculate that the conditions within this subsurface ocean could potentially be suitable for the emergence of microbial life. Unfortunately, if there were life to be found, either on the surface or below, we will have to wait for quite some time, as there are no planned missions specifically designed to investigate this possibility in the near future. Jupiter's moon Europa, with its well-established subsurface ocean, is currently considered a more likely candidate for life detection and is slated for investigation in the foreseeable future. Despite its differentiated interior, Titan does not generate its own significant magnetic field. However, Titan is still quite protected from the harsh solar wind because approximately 95% of its orbit around Saturn keeps it well within Saturn's own vast and powerful magnetosphere. Titan completes one orbit around Saturn every 15 days and 22 hours. Its orbit also has a rather large orbital eccentricity, meaning its path is not perfectly circular, but rather slightly elliptical. Its orbital plane is also at a noticeable angle relative to Saturn's equator. But this doesn't necessarily mean that Titan is likely a captured object pulled in from elsewhere. Rather, much like Jupiter's Galilean moons, it is theorized that Saturn also had several other large moons in its distant past. However, most of these hypothetical moons are thought to have been destroyed through massive collisions early in the system's history, leaving Titan as the lone, victorious survivor. Saturn's medium-sized moons, such as Iapetus and Rhea, are generally believed to be the scattered remnants of this tumultuous early period. Titan's day, much like the day on our own moon, is identical in length to its orbital period. This means that Titan's rotation is tidally locked to Saturn, and it always presents only one face to the planet. Not that, from an outside visual perspective, this makes any real difference. Titan's thick, hazy atmosphere completely blocks any view of its surface from an external vantage point. On the other hand, if you were standing on Titan's surface, you might just be able to faintly discern Saturn in the sky, although the view would be significantly obscured by the constant haze. This tidal locking does mean, however, that if you were to stand in one fixed spot on Titan, Saturn would never move in the sky. It would remain perpetually fixed in one position. if we could somehow magically remove Titan's obscuring haze, this is what the view of the planet would look like. This leads us directly to one of the topics that truly sets Titan apart from all the other moons in our entire solar system: its substantial, dense atmosphere. I vividly remember the first time I ever saw a photograph of Titan. I was genuinely amazed, as it had never occurred to my younger self that a moon could even possess an atmosphere. I initially thought it must have been a newly discovered planet or something similar. To me, what looks particularly odd about its atmosphere is just how far it stretches out into space. When you observe a picture of Earth, you see that our atmosphere fits quite tightly around the planet. Titan, on the other hand, appears to be wrapped in a thick, expansive blanket. There are several reasons for this striking difference. The first is that Titan is considerably smaller than Earth, yet its atmosphere is 1.9 times more massive than Earth's, or 7.3 times more massive when compared on a per-surface area basis. The second reason is that Titan's gravity is significantly weaker than Earth's, meaning it doesn't pull down on its atmosphere as strongly. The sheer mass of the atmosphere actually means that the pressure at Titan's surface is 1.45 atmospheres, or 45% more than the atmospheric surface pressure here on Earth. Comparing the two, you can clearly see the immense extent to which Titan's atmosphere stretches out into space. A height of 600 kilometers is merely the upper limit of its mesosphere. By contrast, ends at around 120 kilometers. Even at a distance of 975 kilometers, the Cassini spacecraft had to make precise adjustments to maintain a stable orbit against the subtle but persistent atmospheric drag when it made its closest approaches. Like the planet Venus, Titan is a superrotator, meaning its atmosphere rotates much faster than the solid body of the Moon itself. This phenomenon is especially noticeable at the Moon's poles. Each pole features a powerful polar vortex that completes a rotation once every 9 hours, a stark contrast to the Moon's own rotational period of 16 days. These polar vortices appear to be like permanent, swirling hurricanes of atmospheric gases. So, what exactly does this atmosphere consist of, and why does it have that distinctive orange color? Well, the atmosphere is an astonishing 98.4% nitrogen, with the remainder being primarily methane and small amounts of hydrogen. There are also trace amounts of various hydrocarbons, which are formed from the breakdown of methane in the upper atmosphere due to exposure to ultraviolet light from the sun. And it is these complex hydrocarbons that are thought to give Titan its characteristic orange hue. This constant breakdown of methane into hydrocarbons should, theoretically, have depleted the Moon of all its methane within about 50 million years. This is an incredibly short span of time when compared to the vast age of our solar system. This fact implies there must be an active source that continuously replenishes the methane. The most likely candidate for this replenishment is cryovolcanoes, which erupt a mixture of water and ammonia from beneath the surface. Although, it's worth noting that even biological life, while speculative, has not been entirely ruled out as a potential source. The methane present in Titan's atmosphere creates a significant greenhouse effect. Without this, the temperature on Titan would be considerably lower. Conversely, however, the thick haze also reflects a large portion of the incoming sunlight back into space, creating an anti-greenhouse effect that cancels out some of the potential warming from the methane's greenhouse effect. All these factors combined mean that while Titan's upper atmosphere receives only about 1% of the sunlight that Earth does, due to its immense distance from the Sun, the surface of Titan ultimately only receives about 0.1% of that sunlight. The Huygens' probe team famously compared the difficulty of taking photographs at this low light level to trying to capture images of an asphalt parking lot at dusk. All these environmental factors mean that while it would certainly be dark on Titan's surface, a human explorer would only require an oxygen mask and extremely warm clothing to be relatively comfortable while standing there. It truly is incredibly cold on Titan, with an average surface temperature of 180 degrees Celsius. This means that any water present on Titan remains perpetually solid. It never melts, evaporates, or sublimates into a gas. So, then, why are there sometimes clouds visible on Titan? Well, these are not clouds made of water ice, but rather methane clouds, which means, yes, it can actually rain liquid methane on Titan. In fact, the temperature on Titan is just right for methane to exist in a liquid state. Methane freezes at 182.5 degrees Celsius and boils at 161.5 degrees Celsius. This specific temperature range, combined with the surface pressure, got scientists incredibly excited about the prospect of finding hydrocarbon lakes, or seas on the surface of Titan, similar to the water lakes and seas found here on Earth. If there really were lakes on this moon, it would represent the first time such features had ever been observed outside of Earth. This prospect was actually one of the main driving forces behind the ambitious Cassini-Huygens mission, to see what truly lay beneath that thick, obscuring atmosphere. The Huygens probe, named after the astronomer who discovered Titan in 1655, was specifically designed to enter Titan's atmosphere and then land on its surface. The possibility of it even landing directly onto an ocean was taken into careful consideration during its extensive design process. As the probe descended, its parachute deployed, and after an almost 3-hour journey through the atmosphere, it finally came to rest on the solid surface of Titan. Sadly, it wasn't able to directly observe any large, active lakes at its landing site. However, what it did see strongly confirmed that methane lakes had once existed there, as Huygens landed on what appeared to be a dried, up-lake bed. These fascinating stones you see in the surface photos are rounded, much like the pebbles and stones found in a riverbed or a lake on Earth, clearly shaped by the flow of liquid. Cassini, from its orbital perspective high above the Moon, was later able to confirm that active methane lakes and seas are indeed still found on Titan today. Near the Moon's south pole, Cassini observed a significant area which was later definitively confirmed to be a lake called Ontario Lacus. It is about 20% smaller than its North American namesake, Lake Ontario, so in other words, it is still a very substantial body of liquid, covering an area of approximately 15,000 square kilometers. On one side of this lake, you can clearly see a smooth shoreline, visibly eroded by wave action. On the west side, scientists observed the first clear evidence of a river and a delta system on Titan, meaning that liquid hydrocarbons flow down from higher planes into the lake, depositing deltaic sediments in much the same process you would find occurring here on Earth. Ontario Lacus is remarkably shallow, estimated to be only between 40 centimeters and 3 meters deep, with the deepest point likely just over 7 meters. As Cassini's radar meticulously mapped this lake, it found that the lake did not have waves larger than about 3 millimeters, meaning its surface would have appeared like a perfectly smooth sheet of glass or a mirror. This doesn't necessarily mean that there can't be bigger waves on Titan, unless this liquid is particularly viscous. But the more likely explanation is simply that it wasn't a windy day when the observations were taken. Given Titan's atmospheric density and lower gravity, waves should theoretically be larger on Titan than they would be on Earth under similar wind conditions. As the Moon's North Pole began to emerge from a 15-year-long winter, another significant lake was discovered, Jingpo Lacus. As Cassini was passing by the Moon, sunlight was reflected off the incredibly smooth surface of Jingpo Lacus, directly into Cassini's view, much like a mirror. Upon further observation, Cassini was able to detect additional evidence of moving liquid on Titan, as clearly seen by the various rivers flowing into this lake. The second largest lake discovered on Titan is Ligeia Mare. Found in the Moon's northern polar region, it is even larger than Lake Superior on Earth, with a surface area of 126,000 square kilometers. While some parts of this vast lake are reasonably shallow, its average depth is considerably greater than Ontario Lacus, reaching about 50 meters, and some sections could potentially reach depths of over 200 meters. Many rivers can be seen flowing into this immense lake, and there are large islands scattered around this area. A particularly curious observation made by Cassini, affectionately dubbed the Magic Island, involved the mysterious appearance and disappearance of what seemed to be an island-like feature within Ligeia Mare. Although scientists are still unsure exactly what caused this phenomenon, theories include suspended silt within the lake, rising bubbles of gas, or perhaps even subsurface ice rising to the surface as the lake warmed during the Moon's spring season. It remains a very curious puzzle. The largest lake on Titan, covering an astonishing 400,000 square kilometers, is the Kraken Mare. As you can observe, this enormous lake is split into two main parts, separated by a relatively small, narrow stretch of liquid quite similar to Earth's Strait of Gibraltar. This narrow section has been nicknamed the Throat of the Kraken because of powerful tidal forces and the sheer size of the lake. It's thought that the tide changes by about 1 meter, meaning this strait may experience strong currents and even powerful whirlpools. Kraken Mare is also quite deep compared to Ontario Lacus, but it doesn't appear to be any deeper than about 170 meters. So, we now know a great deal about the lakes on Titan, but what other interesting surface features might this moon possess? Well, plenty, actually. Titan's solid surface is considered quite young, perhaps as young as 100 million years old. This relative youth implies that its surface must be geologically active, meaning it's constantly being reshaped and renewed. Some scientists believe that the dirty ice crust of Titan is substantially rigid, implying that large-scale tectonic plate movements are unlikely. However, there is some evidence to suggest that localized tectonic activity does occur on the Moon, possibly caused by the powerful tidal forces exerted by Saturn. The primary factor contributing to a continually renewed surface, however, is likely the same process that replenishes methane in the atmosphere cryovolcanoes. Now, this is truly interesting. You know how magma here on Earth is incredibly hot when it erupts from the ground, but then it quickly cools and freezes into solid rock. Well, Titan experiences a very similar phenomenon, except its magma is a mixture of water and ammonia. And when this icy mixture erupts from cryovolcanoes and spills over the landscape, it too freezes, effectively renewing the surface. Because a water and ammonia blend is considerably less viscous than molten rock lava, it flows much further across the landscape than lava on Earth typically would. This means that mountains formed by cryovolcanic activity on Titan tend to be more flat and widespread, and they never reach the towering heights of volcanoes found here on Earth. While it's challenging to definitively confirm specific cryovolcanoes on Titan due to the perpetual obstruction caused by its thick atmosphere, the most likely candidate is a feature called Sotra Patera, located in the southern hemisphere. In some images, where the height has been exaggerated by a factor of 10, Sotra Patera provides a good visual representation of the scale of these dome-like structures and the 1.7-kilometer deep pit at its center, which is the largest known on Titan. The force required for such a structure to erupt would have been immense. And while it doesn't appear to be actively erupting now, it is being closely monitored by scientists. The fact that the lava on Titan is a mixture of water and other minerals means that its surface could be compared to what we might call dirty ice. Because we know that the Huygens probe bounced and wobbled in a specific way as it landed on Titan, we have a rough idea of what the consistency of the surface might be like. Scientists have likened it to a soft, damp sand. Another theory suggests that it's similar to snow with a thin, brittle crust on top. Imagine walking on frozen snow. If you're careful, you can walk on a solid surface. But if you stomp too hard, you will sink in quite deeply. Titan's surface is believed to be something akin to this. Titan's highest mountains are found in the form of ridge belts, much like the Rocky Mountains here in America. These long, linear mountain ranges could also be a form of cryovolcanic activity. The largest mountain on Titan can be found within one of these impressive mountain ranges, known as Mithrim Montes, and it stands at a height of 337 meters. Interestingly, mountains of this stature on Titan are thought to be topped with methane snow, adding another unique element to this already alien landscape. Also found on Titan are many gorges, deep valleys, and extensive dune fields. Using infrared cameras to peer through the atmospheric haze from space, scientists have prominently observed large patches of dark terrain. Originally, these dark areas were thought to be vast seas, until the Huygens probe landed on one of these regions, known as Shangri-La. It turns out they may well have been seas in the distant past, but now they are expansive plains of dark mineral deposits, similar to the Namib Desert on Earth, where they appear as windswept dunes in some places. Overall, Titan can be compared to Earth in many fascinating ways. Scientists even speculate that Titan might show signs of what early Earth could have been like, albeit in a much colder environment. It's fair to say that Titan is remarkably interesting, and I can only hope it receives its own dedicated mission one day. Cassini certainly did an exceptional job, but it was never intended to be a long-term Titan orbiter, and its mission has, unfortunately, already concluded. What I would personally find extremely fascinating is to explore more of its diverse surface. And hopefully, it won't be too long until a mission designed to do just that is approved. Until then, we've covered everything you could possibly want to know about Titan. It has now been 3 years since the Cassini mission concluded its incredible journey by deliberately diving into the atmosphere of Saturn. Its mission was a tremendous success, and in my personal opinion, it stands as one of the greatest space missions of all time. The sheer volume of data it collected over its 13 years in orbit around Saturn is still being meticulously analyzed today, as there remain a great many unsolved mysteries about Saturn and its fascinating moons. One of the most impressive discoveries made by Cassini was the confirmation of the existence of stable liquid methane lakes and seas on the solar system's most unusual moon, Titan. But simply knowing they are there didn't immediately help scientists answer the fundamental question of how they came into being. However, now, scientists may finally have come up with a compelling answer. There are only 2 places in the entire solar system that are known to have stable bodies of liquid on their surfaces: Earth and Titan. That doesn't mean they are very similar places, though. Earth is a rocky planet with a molten iron core and a silicate mantle. Titan, on the other hand, is an icy world. Its crust and mantle are primarily made up of water ice, with a vast subsurface ocean of water and ammonia surrounding a rocky core. This fundamental difference means Earth is much denser, and coupled with its larger size, the gravity on Earth is considerably stronger than on Titan. Both worlds do possess dense atmospheres, but due to their differences in gravitational pull, Earth's atmosphere hugs the planet tightly. Titan's atmosphere, although slightly more massive in total than Earth's, stretches hundreds of kilometers above the Moon's surface, creating that characteristic thick, hazy blanket. Their compositions are also vastly different. Earth is much closer to the Sun, meaning it is significantly warmer than Titan, which allows for an active water cycle involving liquid water, evaporation, and precipitation. Water on Titan, however, is perpetually frozen solid. Yet, The temperature on Titan is precisely right for liquid methane to be present on its surface. This means, yes, Titan experiences a methane cycle in a fashion remarkably similar to Earth's water cycle. Methane clouds have been frequently spotted in Titan's atmosphere, and these clouds release liquid methane onto Titan's frigid surface as rain. This process actively carves out rivers and channels through the surface ices, which then flow into smaller seas or larger lakes. Radar data from Cassini, vividly visualized in these images, clearly show various riverbeds and intricate valleys cut away by the flowing methane. The most prominent of these flow channels are found around Titan's second largest lake, Ligeia Mare. These particular channels, affectionately dubbed vid flumina, are special because they appear to be much older than any other flow channel observed on the Moon. The canyons boast walls hundreds of meters tall with very steep slopes. Liquid methane is visible within the canyon, but at present, it does not appear to be actively flowing. Instead, it is likely a drowned river valley, submerged due to the current level of Ligeia Mare, although some higher altitude tributaries are probably still flowing down into the main canyon. The lakes on Titan can be truly enormous. The biggest one, the Kraken Mare, is larger than the Caspian Sea here on Earth, covering an area of roughly 400,000 square kilometers. The radar data suggests that many of these lakes are quite shallow, some of them only a few meters deep. Some of the larger ones, however, can reach depths of over 200 meters. All in all, this puts the total estimated amount of potential fossil fuels in the form of liquid hydrocarbons on Titan at over 300 times the proven reserves here on Earth. The surface of Titan's lakes is surprisingly still. Some lakes exhibit ripples no larger than about 1 millimeter, meaning they would appear like a perfectly smooth sheet of glass or a mirror. This came as a surprise to scientists who had anticipated waves of up to a meter in height, given the low gravity and dense atmosphere that could theoretically create significant wind-driven waves over the surface. This unexpected stillness could mean that there simply happened to be no wind when Cassini passed over. Alternatively, the liquids might be far more viscous than expected, or perhaps the lakes occasionally freeze over, creating a smooth icy surface. One other intriguing theory has been proposed that dense aerosols, tiny suspended particles, may sit on the lake's surface, forming a thin film that actively prevents waves from forming. The detection of these lakes on Titan would not have been possible without the invaluable aid of Cassini's sophisticated radar instrument and its infrared camera, both designed to peer through Titan's thick, obscuring haze. These instruments utilize a process called specular reflection to make their observations. The radar instrument initially detected large, dark patches across the surface, which were later confirmed to be lakes by the infrared camera when sunlight reflected off the liquid surface directly into Cassini's view, much like what you sometimes see of Earth from space. Specular reflection, using the infrared camera and the sun, ultimately became a frequently used method to confirm what the radar's own specular reflections were indicating. Interestingly, clouds and the subsequent effects of their methane rain were also detected. In one image, you might see a light patch indicating dry ground, but a year later, the same area was imaged again, and this time darker patches are clearly visible, indicating a very flat surface, highly likely to be shallow and small lakes. The lakes aren't distributed evenly across the Moon. Instead, most of them are found concentrated near the poles. However, the Huygens probe, which was part of the Cassini mission and successfully landed on Titan's surface near the equator, did observe clear flow channels around the equatorial regions as well. But where are the lakes these channels would have flowed into? Well, this is thought to be the result of seasonal variations, much like how summer and winter produce different types of weather here on Earth. At certain points in Titan's long year, which lasts 29.5 Earth years, rain would fall in these equatorial parts and temporarily pool on the surface. However, these temporary lakes probably evaporate during the rest of the year, and the liquid water then migrates to the northern and southern polar regions, which is precisely what Cassini and Huygens would have observed during their operational period. Even though Cassini was in orbit around Saturn for 13 years, that's not even half of a full Saturnian year. So Cassini didn't capture a complete picture of all the potential seasonal variations across the entire moon. The lakes likely vary significantly in depth throughout Titan's year, with some potentially drying up completely during certain seasons. There is one other mystery that arose from the Cassini data concerning Titan's lakes that may have recently been solved. Some of Titan's smaller lakes have very steep, elevated rims that tower above the liquid level. This is unusual, as lakes on Earth typically form from erosion processes and the dissolving of limestone, which usually results in shallow, smooth rims. These are often called karstic lakes. However, this common Earth-like process doesn't adequately explain the formation of a number of Titan's lakes. Scientists now believe that these could actually be explosion craters that have since filled up with liquid methane. Models suggest that Titan was once a colder world, experiencing nitrogen rain and snow instead of methane precipitation. This liquid nitrogen would have gradually seeped into the moon's crust, creating vast pockets of trapped liquid nitrogen. As the powerful greenhouse gas methane was slowly pumped into the atmosphere by cryovolcanoes in Titan's distant past, the entire world warmed up. This warming would have caused the liquid nitrogen, now trapped under the surface, to evaporate and expand, building immense pressure within these pockets until the lid essentially blew off, leaving behind a distinctive explosion crater that subsequently filled with liquid methane. There is still a vast amount to be learned from the immense Cassini data archives. The lakes of Titan were just one small, albeit spectacular, aspect of the mission, and scientists are going to be meticulously piecing together these complex puzzles for many years to come, constantly improving our understanding of the Saturn system as a whole. I genuinely hope that future space agencies will be as ambitious and as successful as the Cassini mission was. There is still an awful lot to discover out there in our universe. Let's now turn our attention to Enceladus, perhaps one of the most intriguing and scientifically compelling objects in our entire solar system. And yet, it is only the sixth largest moon of Saturn, and in natural visible light, it appears quite unassuming, a small, bright sphere of ice. However, there is so much more to Enceladus than initially meets the eye. It is an incredibly active icy world, famous for its powerful jets of water vapor that continuously pour out from its southern hemisphere. Thanks to the truly remarkable Cassini mission, we have studied and observed Enceladus in exquisite detail, and perhaps know more about it than even some of the closer and considerably larger Jovian moons. However, even though we've seen a great deal from its exterior, it's the interior of this moon that still holds so many profound mysteries, secrets waiting to be unlocked. Let's first discuss where Enceladus fits into our vast solar system. Enceladus is currently Saturn's 14th closest moon. I say currently, because Saturn has a number of tiny moonlets hidden within its rings that may or may not be officially classified as moons in the future. It is, however, the second closest major moon, surpassed only by Mimas. This means that its orbit takes it just outside of Saturn's primary, major rings. Its orbit precisely follows the plane of these rings, and it takes a mere 33 hours to complete one orbit around Saturn. Interestingly, it is locked in a 2/1 orbital resonance with Dione, which is Saturn's fourth closest major moon. In simpler terms, Enceladus orbits twice around Saturn in the exact same amount of time that Dione completes just one orbit. This specific orbital resonance is believed to prevent Enceladus's orbit from ever becoming perfectly circular, a characteristic that causes Enceladus to undergo continuous tidal deformation. This process is incredibly significant, as these powerful tidal forces generate substantial heat within Enceladus's core. You see, as far as we can tell from observations, Enceladus's surface is predominantly made of incredibly clean water ice, with certainly very little to no visible rocks or other materials present. Because Saturn is situated so far away from the Sun, the outer layer of water on Enceladus has long since frozen over. Enceladus is, in essence, a frozen ocean world, a giant ball of water ice. Because it is so remarkably free from other contaminating materials on its surface, the Moon is one of the whitest objects in the entire solar system, boasting a bond albedo of 0.81. This is almost as high as freshly fallen snow. As such, it is also one of the coldest satellites of Saturn, with a noon temperature of around 200 degrees Celsius. Precisely because the brilliant white color of its surface reflects such a large percentage of the incoming sunlight back into the cold expanse of space. However, approximately 30 to 40 kilometers down under the surface of Enceladus, immense pressures begin to build. The heat energy generated from the constant tidal deformation of its orbit, caused by that resonance with Dione, has increased the temperature of the water ice to a critical point. At this depth, the water can actually exist in a liquid form. It could very well be that there is an entire mantle, a vast global ocean of liquid water, upon which the outer icy crust is resting. This situation is remarkably similar to the magma mantle that our own rocky crust here on Earth rests upon. At the very least, scientists confidently expect there to be a huge, localized pocket of liquid water directly beneath the Moon lava. It flows much further than lava does on Earth. This means that any mountains formed by cryovolcanic activity on Titan are generally more flat and never reach the towering heights of volcanoes we see on Earth. While it's often hard to definitively confirm specific cryovolcanoes on Titan, due to the constant obstruction caused by its thick atmosphere, the most likely candidate identified so far is Sotrapattara, found in the southern hemisphere. In available images, where height has been exaggerated by a factor of 10, it still gives a good idea of the sheer scale of the dome and the 1.7-kilometer deep pit, which is the largest known on Titan. The force necessary for such an eruption would have had to be incredible, and while Sotrapattara doesn't appear to be active right now, it is being actively monitored for any changes. The fact that lava on Titan is a mix of water and other minerals means the surface could be compared to a kind of dirty ice. Because we know the Huygens probe bounced and wobbled in a very specific way as it landed on Titan, we have a rough idea of what the consistency of the surface might be like. Scientists have often referred to it as a soft, damp sand. Another theory suggests that it's like snow with a thin, icy crust on top. Imagine walking on frozen snow here on Earth. If you're careful, you can walk on a solid surface, but if you stomp too hard, you will sink in quite deeply. Titan's surface is believed to be something akin to this. Titan's highest mountains typically come in the form of ridge belts, much like the Rocky Mountains here in America. These ridge belts could also be a form of cryovolcanic activity, where icy magma is pushed up through cracks in the crust. The largest known mountain on Titan can be found in one of these impressive mountain ranges, known as Mithrim Montes, and it stands at a height of 337 meters. Interestingly, mountains of this height on Titan are thought to be topped with methane snow. Also found on Titan are many deep gorges, winding valleys, and vast dune fields, which can be observed using infrared cameras to peer through the atmospheric haze from space. What can also be seen quite prominently are these large, expansive patches of dark terrain. Originally, These dark patches were actually thought to be seas, until the Huygens probe landed on one of those very areas known as Shangri-La. While they could well have been seas in the distant past, they are now understood to be plains composed of dark mineral deposits, very similar to parts of the Namib Desert on Earth, where they appear as windswept dunes in some places. Overall, Titan can be compared to Earth in many fascinating ways. Scientists even think that Titan shows signs of what early Earth might have been like, albeit in a much colder environment. It's fair to say that Titan is remarkably interesting, and I can only hope it gets its own dedicated mission one day. Cassini did an incredible job, but it was never solely a Titan orbiter, and its mission has now concluded. What I would find extremely fascinating is to explore more of its surface directly, and hopefully, it won't be too long until a mission designed to do just that will be approved. Until then, we've covered everything you could possibly want to know about Titan. It has now been some years since the Cassini mission concluded its incredible journey by purposefully diving into the atmosphere of Saturn. Its mission was tremendously successful, and it was, in my opinion, one of the greatest space exploration missions of all time. The sheer volume of data it collected over its 13 years in orbit around Saturn is still being meticulously analyzed today, as there are still many unsolved mysteries about Saturn and its diverse family of moons. One of the most impressive discoveries made by Cassini was the confirmation of the existence of liquid methane lakes on the solar system's most unusual moon, Titan. But simply knowing they are there didn't immediately help scientists understand how they came into being. However, now, scientists may have finally come up with a compelling answer. There are only two known places in our solar system that possess stable bodies of liquid on their surfaces, Earth and Titan. That doesn't mean they are very similar places, though. Earth is a rocky planet with a molten iron core and a silicate mantle. Titan, by contrast, is an icy world. Its crust and mantle are made up primarily of water ice, with a vast subsurface ocean of water and ammonia surrounding a rocky core. This structural difference means Earth is much denser, and coupled with its larger size, the gravity on Earth is considerably stronger than on Titan. Both worlds do have dense atmospheres, but due to their differences in gravity, Earth's atmosphere stays relatively close to the planet. Meanwhile, Titan's atmosphere, although a little more massive in total than Earth's, stretches hundreds of kilometers above the Moon's surface. Their atmospheric compositions are also vastly different. Earth is much closer to the Sun, meaning it is much warmer than Titan, which allows for a vigorous water cycle. Water, as we know, is frozen solid on Titan. However, the temperature and pressure are just right for liquid methane to be present on its surface. That means, yes, Titan experiences a methane cycle in a remarkably similar fashion to Earth's water cycle. Methane clouds have been frequently spotted in Titan's atmosphere, and these clouds release liquid methane onto Titan's frigid surface as rain. This process carves out intricate rivers through the surface ices that then flow into smaller seas or lakes.